Hello everyone, Robert Wilson here. I'll be presenting my project on earthquake magnitude classification and prediction using machine learning. I will discuss how I developed a digital twin to classify and predict earthquake magnitudes using real-time seismic data from the U.S. Geological Survey, which is a science agency that provides scientific information about earth, water, and biological resources. The objective of this project was to develop a digital twin that accurately classifies and predicts earthquake magnitudes using seismic data features such as latitude, longitude, and depth. I employed random forest models for both classification and regression tasks on real-time earthquake data obtained from the USGS API. The models were evaluated using various performance metrics, and statistical hypothesis testing was conducted to assess their effectiveness. The results showed high accuracy in classification and prediction, confirming the model's effectiveness through statistical significance. Earthquakes pose significant risks globally, and timely classification and prediction are crucial for disaster preparedness and response. The key question I aimed to answer with this digital twin was, can seismic data features such as latitude, longitude, and depth be used to accurately classify earthquakes into magnitude categories as measured by the performance metrics of a machine learning classifier? For this presentation, we'll be covering these topics here. All right, first let's take a look at the data stream and the handling of the information. For this project, I utilized the real-time earthquake data provided by the United States Geological Survey Earthquake API, which offers data in a GeoJSON format. This data includes information on all earthquakes reported within the past month and is updated every 60 seconds. The data handling process involved several key steps. First, I extracted essential features such as magnitude, place, time, latitude, longitude, and depth from the GeoJSON data. The timestamp was converted to a readable date-time format. Next, I cleaned the data by dropping rows with missing values in critical fields like magnitude, latitude, longitude, and depth to ensure data quality. Then I performed feature engineering by creating a categorical variable mag category by binning magnitudes into 4 different categories. Minor for magnitudes less than 3, light is 3 to 4, moderate is 4 to 5, and strong is 5 and above. These steps ensured that the data set was well prepared for training the machine learning models. In the feature engineering phase, I focused on selecting and transforming the data to optimize model performance. The features selected were latitude, longitude, and depth, as they are directly related to the seismic activity's location and intensity. The target variables were the feature mag category for classification and magnitude for regression. Data transformation involved converting the categorical target variable mag category into numerical labels such as 0, 1, 2, and 3. Using label encoding, which is necessary for training classification algorithms. I also applied standard scaling to the features, ensuring that each feature contributes equally to the model's learning process. By carefully preparing the data, I aim to improve the accuracy and efficiency of the overall models. I implemented 2 main machine learning models in this project. The first was a random forest classifier, which aimed to classify earthquakes into their respective magnitude categories. The training process involved splitting the data set into an 80% training data and a 20% testing set, training the classifier on the training data and evaluating it on the testing set data. The second model was a random forest regressor, intended to predict the continuous magnitude values of the earthquakes. The same data split was used for consistency. Both models leveraged the selected features and trained to capture the underlying patterns in the seismic data. The random forest algorithm was chosen for its robustness and ability to handle nonlinear relationships. After training the models, I evaluated their performance using the appropriate metrics. For a classification model, I used a confusion matrix to assess its ability to correctly classify earthquake magnitudes. The high values along the diagonal indicate accurate predictions. Misclassifications were minimal and mostly occurred between adjacent categories, which is understandable given their similarities. For the regression model, I evaluated it using the mean squared error and R-squared score. The regression mean squared error was 0.2708, and the regression R-squared score was 0.8411. A low mean squared error indicates that the model's predictions are close to the actual magnitudes, and the R-squared score of 0.8411 suggests that approximately 84% of the variance in earthquake magnitudes is explained by the model. These results demonstrate that both models performed well in their respective tasks. The next step is model validation and improvement. And to validate and improve the models, I undertook several steps. I performed k-fold cross-validation to ensure that the models generalize well to unseen data, which helps assess their robustness across different subsets of the data. I experimented with different numbers of estimators and tree depths in the random forest models, selecting the combination that yielded the best performance without overfitting. Next, I analyzed the importance of each feature in the models and confirmed that all three features, the latitude, longitude, and depth, significantly contributed to the predictions. Additionally, I applied PCA, or principal component analysis, to reduce the feature space and visualize the data distribution, which helps in understanding the data's variance and potential patterns. These efforts enhance the model's accuracy and reliability. Next is the analysis of our results. To statistically validate the model's performance, I conducted hypothesis testing. For the regression model, I formulated the null hypothesis that there is no significant difference between the predicted and actual earthquake magnitudes. The results of the paired t-test were as follows. There was a mean difference of 0.0122, a standard deviation difference of 0.5204, and a t-statistic of negative 0.9216. And finally, the p-value of 0.3569. Since the p-value is greater than the significance level of 0.05, we fail to reject the null hypothesis. This indicates there is no significant difference between the predicted and actual magnitudes, confirming the model's accuracy. For classification model, I tested whether the model's accuracy is significantly higher than the random chance. Statistical tests confirmed that the model's accuracy is significantly higher than baseline accuracy, allowing us to reject the null hypothesis in favor of the alternative. These statistical analyses proved strong evidence of the model's effectiveness. In addition to model evaluations, I identified high-risk areas based on the data. While my code presents a map of all earthquake data and annotation for the whole world, Japan has the highest level of strong classified earthquakes when compared to other regions in the gathered data. Identifying high-risk areas can assist authorities and researchers in focusing monitoring and preparedness efforts. Overall, the classification model successfully classified earthquakes with high accuracy, and the regression model provided accurate magnitude predictions with low errors. These findings support the potential of machine learning models in earthquakes analysis. Graphs of the data reveal a few valuable pieces of information. As expected, the majority of earthquakes are between 1 and 3. This distribution reflects the expected trend where smaller earthquakes are far more common than larger, more catastrophic ones. For a classification model, the ROC curve demonstrates the model's ability to distinguish between the different earthquake magnitude categories. The areas under the curve, or AUC, values for classes like minor, moderate, and light are very high, ranging from 0.88 to 0.99. Even the strong and less frequent magnitude classes have strong AUC scores of around 0.85. This highlights the model's excellent classification performance and the ability to effectively separate the magnitude categories. For the regression model, we can use the actual versus predicted earthquake magnitudes. The scatter plot demonstrates the clear alignment between the actual and predicted magnitudes. While there is some variability, the overall trend shows that the model consistently captures the relationship between the seismic features and the earthquake magnitudes. This is further supported by the low mean square error of 0.2708 that we previously saw, and the high R-squared value of 0.8411 that we previously saw. Together, these visualizations validate the effectiveness of both the classification and regression models in analyzing earthquake data. The results highlight the model's strong predictive accuracy and their ability to deliver meaningful insights for earthquake classification and prediction. The digital twin developed in this project effectively utilizes seismic data to classify and predict earthquake magnitudes. Both the classification and regression models demonstrated high accuracy and reliability, with statistical tests confirming that the model's performance is significantly better than chance. The models can enhance real-time seismic event analysis and assist in identifying high-risk areas, thus contributing to better disaster preparedness and resource allocation. Deploying the digital twin in collaboration with seismic monitoring agencies and integrating it into early warning systems can provide timely alerts and further enhance its practical impact. This project demonstrates the valuable role that machine learning can play in understanding and mitigating earthquake risks.